Hey everyone, we are group 115 and today we are here to give our final project update on data-driven approach for battery life cycle prediction. I am Bhavya, I am a PhD student in Department of ECE and today with my group mates Afra Anzum and Hari Chandana, we are gonna give our final update.
So, why batteries? Because batteries are more important in wearable technologies, implantable medical chips, and the smart textiles. And it has been seen that in 2026, the market will reach about 65.4 billion. So it is very important to predict the life cycle of the battery and the capacity of the battery to reach this technology more efficient. So there are lots of challenges outside there. The most important challenge is it is very complex, non-linear degradation pattern, and it also require unlimited availability of the large, high-quality dataset. So we came up with a plan to fix most of these problems by integrating the multiple channel battery profile, such as current, voltage, temperature, to predict the capacity and the state of the health of the battery. Also, we have a plan. We utilized data augmentation technique to address the data scarcity in the medical device industries, and we aims to extend the battery life in wearables by up to 20% through the optimized users patterns. So we used NASA's battery dataset where the battery has 2 ampere hour capacity and every battery has 160 cycle. So the upper voltage was around 4.2 volt and the lower voltage was 2.7 volt. Here in the graph, we can see 4 different battery dataset. The capacity of the every battery was measured with respect to their discharge cycle.
So, using this data set, first we define a baseline using a three-layer LSTM architecture, and we divided the data set into 80-20 testing training data split. And these are results. We characterize the result in terms of MSE, MAE, and RMSE. Although our performance at the baseline was not that great, that's why we switched to a transformer architecture. Transformer is well known to predict long-term dependencies of time-dependent data, so that's why we chose it. We can divide this transformer architecture into four different parts. The first part would be your input and normalization. The second part is the denoising. For denoising, we are using an autoencoder. The third part would be the transformer layers, and finally the predictions. Here for the activation function, we are using ReLU, and we have two feed forward layer and a two multi-head self-attention layer, which is helping us to understand the long-term dependencies of this structure. Using this, we try to predict the capacity over different discharge cycles at different conditions. So this is the output for battery 5 and battery 6 at different temperatures, and we can see a good cross relation between the testing data and the predicted data and the original value of the battery performance. Similarly, these are the values at higher discharge currents. So the earlier results were at 1.5 milliamp, and these are at 3 milliamps. Finally, to better understand the performance of our model, we also compared with a LSTM architecture. So in total, we had three models: the baseline, which is a three-layer LSTM, a eight-layer LSTM, and finally a transformer architecture. For transformer, we use a denoising architecture, and we can clearly see the performance of the transformer was much better than the three-layer or eight-layer LSTM. The reason could be the transformer takes input in terms of packets as compared to LSTM, which takes sequential input. So it's very hard for a LSTM architecture to predict the long-term dependencies, especially if it is changing with respect to time and with respect to different number of cycles. Finally, to conclude, we would say like we used the standard NASA battery data set. We defined three different models. We used Python to run these models in Google Colab, and the first one was three-layer LSTM, the second one was eight-layer LSTM, and finally a denoising transformer with ReLU function as the activation function. The performance with the transformers was much better than the other two methods. Our future plan is to further work on the fine tuning and further extend the scope of data augmentation to increase the amount of data we have, because transformers are like data heavy models. So we need a lot of data, and we have shown good results in this project, and we further plan to extend it in the future. These are our references, and thank you so much. Would be happy to know more questions and suggestions from your side.